Hello, everyone. I'm Professor Shijing Sun from University of Washington. Today, I'm very excited to share a new lecture series on an important application of machine learning in real-life engineering systems, battery lifetime prediction. Over the next few lectures, we're going to go through together how to make sense of battery life data, followed by feature engineering, model selection, and model interpretability. Throughout these topics, you'll find there's an underlying theme going through all of these lectures, which is data-efficient machine learning. So for today, we're going to start to talk about how do we quantify battery degradation, why we want to use machine learning for the task of predicting a battery's lifetime, and how do we construct a data-driven workflow to achieve our predictive modeling goals. Let's dive in. So batteries are everywhere in our life. Whether you are thinking of charging your laptop for work or using your phone to take a beautiful image. You may be driving an electric vehicle, or you're interested in learning more about energy storage at a large scale. So for all these applications of batteries, knowing when a battery will fail has tremendous values to the manufacturers, the engineers and the scientists, as well as to the consumers. So then it comes to the important question of how do we quantify a battery's degradation state. So an important concept within the battery community is capacity. And it is a measure of a battery's electric charge that are stored in the battery. You can calculate the battery's capacity using the integral of current over time. So you'll often see as a battery starts from a new battery to going through its lifetime, you'll see a chart showing in on this slide where we have the capacity as a function of time. So you can imagine over the lifespan of a battery, as we keep using our batteries, the total capacity of a battery, which measures the ability of a battery to store and deliver charges, decreases. And since we often charge and discharge a battery and we call it a cycle, you also see instead of time, people use a cycle number as a measure of the extent of a battery is used. And sometimes you'll see instead of capacity, people state discharge capacity, which indicate the capacity was measured with a battery from its fully charged state to its fully discharged state. So when it comes to tracking a battery's lifetimes, another important concept is state of health. So at a given point throughout a battery's lifetime, state of health is a metric that describes how the current condition of the battery relative to a new battery. So you can calculate the state of health of a battery using the ratio of the current capacity over the nominal capacity, which can the capacity of a new battery, and times 100%. So once you have the idea of using state of health as a metric to track how a battery degrades, another important concept, the third one in this lecture, is something called cycle life. And the cycle life is an end-of-life metric for a battery. So it quantifies the number of the charge-discharge cycles a battery can undergo before its capacity falls below a specific threshold. Within the battery community for electric vehicles application, for example, often we say when a battery reaches its 90% or 80% of state of health, we say the battery is ready to retire and repurpose. So if we consider here, we have 2 points throughout the battery's lifetime. One of them, at this point, we say probably the state of health is around 97%. And later on, the state of health drops to 90%. So you may have already realized this degradation, what we observed throughout the battery's lifetime, is nonlinear. So our goal as a data scientist here is trying to set up a model where we can capture this nonlinearity and allow us to forecast what is the future state of health of a battery with the early state data. So with this idea, it's probably not a surprise. Every day, there are many and many battery aging tests being conducted across the multiple stages of the battery industry. So here, you see, we want to find ways to separate the short-lived battery with the long-lasting batteries at a different stage from when the battery has been originally researched and designed to when the battery has been produced in a factory, to the module and pack assembly stage, to the system integration stage, to the customer usage stage, and finally, when we're considering the recycling and the repurposing of a battery pack. So all these stages, we really use a lot of battery tests to help us understand when a battery will fail. This whole process, as you can imagine, the full aging test until a battery is finally dead can take multiple years. And we cannot just test all the available batteries until it's dead to wait until then to say these batteries are bad. So we really need predictive modeling to help us to forecast the future health of a battery. So this is where the idea of the problem formulation of battery lifetime prediction comes in. So the idea here is that can we stop our battery aging test? Not in the future, not when the battery has finally near its death, but can we stop our battery testing here, early in the process, and then we can save the money and the resources for the later on tests. But at this stage, using our predictive model, we already have an insight of the variety of the possible battery life span in the future. So before machine learning methods will become popular, a lot of the scientists and engineers have been using physics-based modeling to help us to forecast the battery's future state of health. In summary, we can study the battery degradation mechanisms. For example, a battery may have challenges of forming dendrites, structural disorders, and also maybe there are microcrackings. So all these phenomena contributes to the cause of a battery failure, either in near future or in a long term, a lifetime of a battery. If we really think about all these degradation mode and mechanisms, it is inherently very complicated. So if we think about the capacitive fade, which we observe throughout the battery's lifetime, we can attribute the observed capacitive fade as a function of cycle number or time to different degradation mode, and that can be attributed to different degradation mechanisms. So here is a list of 11 different degradation mechanisms reported by the researchers in the paper cited on these slides, and there may be more. And of course, different environmental stresses and different causes from high temperature, different current load can lead to these degradation mechanisms. So at this stage, it's clear. So using the mechanical insight to really simulate how battery would behave over time is very accurate, and it's generalizable because rooted on the fundamental scientific principles and mathematical formulas. But at the same time, it can take a long time to develop these models, because we have to consider different physical phenomena from atomic scale to micro scale to the full device scale, and it can be rather challenging to capture all the details of the physical phenomena. So because of that, a lot of the scientists and engineers start to think about maybe we can replace part or all of these physics-based models with data-driven methods. So in turn, we'll gain the efficiency of using a data-driven model to forecast our future state of health of batteries without having to compute the details of individual degradation mechanisms. So here, our goal to use machine learning is really to accelerate the battery lifetime prediction with accurate estimates of the current and future state of a battery. So instead of just tracking one battery or two battery cells, we collect many battery cells that have a diverse lifespan. And we use machine learning models to really study the early stage of the batteries, and we hope our models can capture the patterns being observed, and then using these patterns to help us to give insight of the future state of the batteries, which leads to their diverse lifespans in the future. So at this stage, we understand our initial data, and we understand our goals. You'll be thinking, so what a battery cycling data look like? So here are a few photos of the battery cyclers. And these photos were taken in the Clean Energy Institute here at University of Washington. So you can see we can test multiple batteries in parallel. And if you look into the data you get from the battery aging tests, you'll probably see something in a tabular form like the ones shown here. So let me pause a moment and to consider the two tables now shown on the slide. So all of them measures the current and the voltage as a function of time. And you can also see we have different cycling numbers as we go through the number of charging and discharging series. So how long does it take you to realize the two tables actually are representing the same data, but just in different formats? So here you can see if we take the raw cycling data directly from the real-life physical systems or physical machines, we often have challenges such as here we have test time in seconds, and here we have test time in hours. So they may be different here in terms of the units. And there may be difference in terms of the headings, so how the current and the voltages are represented. And of course, often when it comes to our recording data, we can also have different tables having different significant figures. So often the first step when we collect the battery cycling data is to actually structure the raw cycling data into a standard format. And this will get us ready to perform the following steps of applying machine learning models. So now we have our data set ready. So moving on, they may be thinking, so our raw data has been collected in terms of current and voltage. How these current and voltage data from our cycler related back to the capacitive phase over time? So here, when we are actually talking about the current data as a function of time, we are talking about data we collected within one cycle. So here you can see at a given point throughout the battery's lifetime, we can check out how the charging and discharging process being applied to a battery. So in this case, we get to see the battery first goes through charging, and then it goes through discharging, forming one cycle's data of battery aging tests. Similarly, instead of current, we also have the recordings of the voltage changing throughout the charging and the discharging processes. So now we have like a lot of like the data collected, sitting like waiting for us to like build our model, and we are ready to build a data-driven workflow to apply machine learning for battery lifetime prediction. So like let's give a few examples as we go through like the data collection process, feature engineering, modeling, and application stages. So to start with, like when we are trying to like build our data-driven workflow, we started with data collection. For example, like we will have our raw cycling data. And in the form of we are tracking the voltage, the current, the temperature, and also the capacity. And of course, we will have our prediction like a target in mind, and these are the health metrics. For example, we can have our model aimed at predicting the cycle life of like a battery. And then when it comes to like a feature engineering step, so once we have like all our raw data, often we need to transform our data into a different format for it to be suitable and appropriate for our models. So in a way, like we change the input of our like model. In this case, when we can look for early features. Specifically, for example, we can look for the change of capacity from the 100th cycle to track it back to the 10th cycle. With the features like collected, we are now ready to input them into our machine learning models. So we may have different goals for our like lifetime prediction. For example, we may be interested in building a classification model where we have two features, feature 1 and feature 2. And we are interested in finding out if we can separate the bad cells from the good ones. We may also be interested in building a regression model. And in this case, we are interested in figuring out if we can accurately predict a health metrics. So for example, the lifetime of a battery we are interested in. So using the data we collected, we try to compare the predicted health metrics with the actual and building our model from there. Batteries have a lot of industry applications. With our predictive models being made, we can use them for a range of different like applications. For example, we can use like the results from our machine learning to help understand whether a battery is ready for its second life applications. For example, like it was a battery used in electric vehicles. Now like we use it for grid storage. We can also apply our machine learning models to new batteries that just came out from like battery manufacturing, and we can use it for quality control, ensuring all the batteries with high predicted lifetime entering the market. Once we have like the data-driven workflow, it is also important to remember that like a battery life prediction shares a similar workflow to like other lifetime predictions for like different energy devices. So we can remember there's a broader context of data-driven life prediction as we can go through a similar pipeline to apply the idea of machine learning in solar cell durability prediction and fuel cell durability prediction, and all of these like contributes to accelerated prediction of lifetimes for energy devices. With that, thank you for listening and see you next time.